Davide Faranda. So Davide comes from Paris, well, actually Saclay, Laboratoire des sciences du climat et de l'environnement. So he's a specialist of theoretical approach using statistical physics and mathematics for climate. So he will speak today about the application of machine learning to decipher the language of atmosphere air masses.
Okay.
It seems you didn't share the correct screen.
In fact, I was thinking that. Let's try again. Screen 2.
We are seeing the screen where you have the two.
Okay, maybe I have to do it. Let's do screen 2 again. Yeah, now it should be fine. Let's try to make the gain to reduce only up.
You haven't shared the screen yet. Okay.
There is some delay, maybe. Okay. Okay, sorry about that. I will try to keep track of the delay. Okay, so good morning, everyone. Thank you very much, the organizer, for the kind invitation. So today I'm going to speak actually about the work of this guy, Luca, who's just sitting there. So he did an internship at LSC. So it's Luca's Ferry. You have his contact here. And during this very fruitful internship, we basically brought from linguistic machine learning technique to climate science. And what is good about this technique, and I spoiler all the presentation, is that there is a lot of interpretability. So we can make the composition of atmospheric flow in some pattern that is very interpretable. And in fact, since we take it from linguistics, that is why you have this kind of poetic title. But you will understand what it means during the presentation. This work has also been done in collaboration with Flavio Bons, who is postdoc at the LSE, Béranger Podouan, who is at the LINSN, and Béranger Dubrul, that many of you know here for other reasons, that is not machine learning. So let's see if I can go to the next slide. As you can see, everything is stuck. Let's try the bar. The bar doesn't work. Okay, good. So what's going on? I don't see my mouse. That's the problem. Okay. So and now that this is back, so maybe I cannot remove it without making a disaster. So I will try to put it here. Okay, but let's see if it works. When we look at the weather map, we have that the normal description that we see at the Chaîne Météo or Weather Channel, whatever you like. We listen to the weather forecast, and the meteorologists tell us, well, there is a low pressure system over the east of the United States, so it's going to rain in New York City, and instead on the Rocky Mountains we have high pressure. So if you visit the Grand Canyon, you are advised to wake up early to avoid the heat wave. It's not the description that we will do when we try to decompose this pattern in the normal framework that we use when we compute, for example, the weather regimes or the EOF or the POD or whatever acronym you like, the Fourier transform of a weather map, because that will give you some signal everywhere. And so you won't listen a meteorologist saying, this is the first component of the Fourier decomposition of the weather today. And then you look and you say like, no, I really don't understand this. So we would like also, when we do climatology, to have a decomposition that we can understand in terms of the object that meteorologists have in their everyday description of the weather. And to do this, I say it again, we should try to give up, and I have always the same problem with the moving the diapo. Okay. We will try to give up but see if we can have something else that can replace the usual decomposition that we do of weather map into weather regimes. And if you're not familiar with that, what we usually do in climate since the 1990, and actually a work that has been done also in my lab, at the EPSL, is that we project a weather map like the one we've seen before into 4 types of typical weather map. And for example, I don't know if you see, this is Europe. I'm trying to point to France here. And we have, let's say, a normal decomposition in 4 possibilities. That is one where we have, these are geopotential height anomaly at 500 hectopascal, but it really doesn't matter. What it matters is that in this decomposition, you have a cyclone between Greenland and Norway, and an anticyclone over Southern Europe. So this is the kind of weather that brings storm in the UK and in Scandinavia. Then we have another pattern here where there is a cyclone, a cyclonic pattern over Europe, and this brings bad weather over Spain, Italy, and France. Then there is another pattern where we have a high pressure system over the Scandinavia, and this is what causes in winter cold spell over Scandinavia and fog over France, for example, and in summer the heat waves, okay? And then we have another pattern that is the ridge, the Atlantic ridge, and this you know because you've seen this guy 2 days ago. This is the one that brings snow well, if it's moving a bit towards the US and Canada, it brings snow over France, otherwise it brings snow over Italy and Greece in winter. So this is the kind of projection that we do, and it lacks sometimes of interpretability because we reduce the phase spacing for this phase space that can have a lot of possibility. And you see from my description, I didn't say many events that can happen in the weather in Europe. I just can categorize some of them. It lacks of interpretability. Why? Because in all these maps we have combination of cyclones and anticyclones, and we don't know if we have change in the projection, what happens, for example, for climate change, what is the right one that we have to choose. Someone is Camelo. So we'll try to replace with the latent Dirichlet allocation that work better as a human meteorologist. Let's see if now it works well. So let's try to follow how we go from linguistic to climate. So in linguistic, this latent Dirichlet allocation is used is a generative probabilistic model to scan large corpora, actually the plural of documents, okay, and understand what they're talking about, okay? So for example, here you have in the corpus is made of documents, and each document is made of words, okay? And these words, as you see, for example, the word orange can be both a fruit or a color, okay? So from the distribution of topic that we get from these documents, we can understand, and then this our task to give the name of the topics, that we have somehow colors, fruit, and seasons, okay? So this help people that do machine learning in linguistics to analyze large text and understand what they're talking about. In the climate, we will move from this description to a description where we extract motifs, and we choose to use the French name because we are proud that we have done this first, that are decomposed. They decompose basically the maps that we were seeing before into local patterns that now are exactly the motifs that the meteorologists tell us at the television. And so for us are very interpretable, even if we do climate. And we will show how we go from this description to this other description. So let's start. And well, I will go a little bit more into detail, but the technique is actually very simple. There's no much mystery. It's exactly the way you will think to do it. So we have to think of documents as bags of words, okay? So each document well, the words belong to a finite vocabulary that is made of n words, and then we have simply the number of occurrences of each word in a document. So documents are represented by vectors DL, okay? With DL, the number of occurrence of WE in the document L. So once we have this, we can do this game, okay? So we can get from, again, the previous example, the topic word distribution with certain weights. For example, blue will have a 0.4 weight in this corpus when it's colors. 0.3 will be red and 0.2 will be orange, but orange also appear in fluids with another weight. Okay, so you see the way how it works, and then you can decide also with this distribution what is in your topics the most important word, what is the least important. So if you want to know that you're talking about season, but you're talking more about winter, you have this information here. Basically, there are mixture of topics, as I was saying. For example, then we can get the document topic distribution. In document 1, we have colors, but also fluid. And we have also the weights of each topic, which is nice because this will be very useful for climate. And again, to make it even clearer, well, if document 1 is word 1, 3, 4, 7, 10, we have the word occurrences. Then we can do all these, go basically from the words of documents to the word of topics, and have from for each word the topics where are associated. So we can have a complex pattern or simple one that tell us that change this word into this word and make this word very interpretable for the humans that then have to use this machine learning technique. Okay, so this was the latent Dirichlet allocation in linguistics, which is, I think, on its own interesting because it means that we're able to scan many documents very easily and get interpretability out of that. So now, how it's done in physics? So the analogy has been proposed in this paper, and in linguistics we have documents. Now in physics, imagine that we have a long data series of maps. Okay, so we have snapshots, so single maps. For example, we will use sea level pressure maps, and then the words are replaced by the grid points. Okay, and each grid points have values, so the number of occurrences will be the grid point values, and the topics we will see that they will correspond to spatial patterns, and we name them motifs. So grid points values need to be converted to positive integers. Remember this idea that we need an alphabet, okay, to construct our words. And then we do, of course, to do this, we do rescaling, digitalization, and thresholding. And an idea that we have to, of course, introduce when we apply to pressure anomaly of the ENSE pre-analysis over the North Atlantic. So our data set will be the daily weather maps over the North Atlantic, okay, spanning 1948 to today. We have to double somehow we have two words, because the words are always, we don't have a negative alphabet, although it would be maybe interesting to do it. When we do it in the world of physics and we have observables that have a sign, we have to split into positive and negative sign, but we will find out that this is actually very useful when we do it for the sea level pressure maps, because we will get separately anticyclone and cyclone. So the first thing that we have to do when we apply this technique is to understand how many motifs we need to describe our field. And one way to do it, so I will show you two ways that Luca tried to extract what is the optimal number of motifs that are in this problem. Remember again that the dataset that we use is the dataset of the sea level pressure maps daily from 1948 to today. This is about 25,000 a database of 25,000 maps. The resolution, also to give you an idea of the spatial resolution, is 2.5 degrees longitude latitude, so it will be 20 times 50 the phase space, let's say, so what we have as number of variables. And you see that when we increase the number of motifs that we ask to the techniques, because we ask a number of motifs, give us 10 motifs, and then we end up with a sort of area for these motifs. And here, the area where we converge has a radius that is a radius of between 1,000 and 1,500 kilometers. That is actually the size of a cyclone. So it has some physical meaning that we can check. Another way that we can do that is more useful, let's say that is more used when we do the composition in general, is how much is the area of the motifs, how many motifs we need to cover the area of the original map, okay? So we can check that also here we start to have some optimum between 20 and then when we are at 30, actually 25, sorry. When we are at 30, we don't add much information. So we can decide that the motifs that we need to study this problem is about 25. Interestingly, this number comes out also from another problem that was the one that we did for another study, that is that one of measuring the dimensionality of the same kind of maps using a technique from dynamical system where this 25 sort is an upper boundary. We don't have more values larger than 25. Actually, already with between 10 and 20, we describe almost all the maps that we have in the dataset. So somehow, actually, we have the 25 was also the number of degrees of freedom estimated with another technique. So we have some confidence that this number that we extract is not just fried air, we say in Italian, but corresponds to some physics of the problem. Okay, so and now I think that you're all very curious to know what are these motifs. Suspense, but I already say. So the motifs are there's an anticyclone and the cyclones with their preferred position in the domain that we have given to the analysis. Okay, so we could name all of them because they have name, but I just put some just to show you. So this guy here is the Siberian High. Okay, so it's an high pressure system over Siberia. This is the Azor anticyclone. So this we always listen. The Azor anticyclone is in its position, blah blah blah. And then there is some other lady, let's say, that is very known. For example, this Icelandic low pressure here, and the Genoa law. And actually today, if you would decompose your field in motif, this will be definitely there as one of the first motif. Okay, so what is important is that when you construct your description in motif, you start with one, okay, the one that has the highest weight. Remember in the idea of the words, winter was the one with the highest weight. So you pick up one, for example, you will pick up the Genoa law, then it will probably give you an anticyclone. Okay, and so when you start to reconstruct, you introduce features that are there. You never add, for example, you imagine that you decompose in Fourier a precipitation field. Okay, you will have precipitation even when it doesn't rain. Okay, instead this prevents. It will only give you something that is there. The Genoa law is there and it will be there. Then the second one will be an anticyclone, for example, that is also there. And the interesting thing is that although you have a list of 28 motifs, for a given day, the first 4 or 5 already gives you an optimal reconstruction of your field. So you have something that is really very interpretable because day by day you end up reading 4 or 5 motifs, but even just the first 2 are the one probably you are interested to read this kind of forecast. Okay, but we are not meteorologists because here you read it's the Laboratoire des sciences du climat so not of meteorology. So why do we care of having these sort of artificial intelligent meteorologists that give us this analysis, okay? But the interesting thing is that this guy give us this distribution for all the day in the database. So he has done the job for 60 years. In how long does it take, Luca, to do? Very little. An hour. In an hour, you can do all the distribution for these 60 years on a single core, basically this. So if we parallelize, it can be even faster, of course. But then, for example, in the database, we have extreme events. So we can check, for example, what is the distribution of motives associated with extreme events. And in the paper, you can find storms, extratropical storms, heat waves, and cold spell. And I will show you the result for cold spell. And what we tried to do with Luca is that there is a very nice database of extreme events that is EMDAT. And this database is constructed based on the impacts. So there is no physics a priori. Someone goes and put their cold spell if there are deaths or let's say damage, important damage caused by the cold spell, okay? So then we take these dates and we try to see if they correspond actually to some kind of motifs that can give us an idea of what do we have to see as a synoptic object, so these cyclones and anticyclone where we have the cold spell. Not that this is a problem in the community, because there are papers that says, very recent paper that say when we take this database, that is now one of the most used, we don't find a nice correspondence between the physics of the extreme events and the damage. So we were wondering if we could find something with the motifs. So that was basically the motivation. So now I will show you. Bear with me, this is a bit of a complex slide, but this is the, let's say, the D-Day, okay, the day 0 of the event. And this is the distribution of motifs with their weight in percentage, okay? And this is the sea level pressure pattern of all the averages of the cold spell. So what you see here, ABC, is the 3 motifs that have the highest weight. And actually, the weight can go up to 10%, okay, for 3 and 2. Note that this is statistically significant because the average weight of the motifs, it's normally about 4%, and they are all equally distributed if we take all the days. So what we can see is that at the day of the event, we already have these 3 hikes that tell us that the dynamics of cold space is not driven in Europe by the low pressure, but actually by the high pressure. So it's a thermodynamic, it's mostly a thermodynamic effect linked to the fact that we have this high pressure building up. We have some snow cover on Scandinavian winter, and we have a radiative effect of the albedo that sends us back radiation at night to space, and we can reach very low temperature. But we can also see, and this is a movie, and now the movie, the challenge is always, can it work? Yes, it works. You see the day from -14 to the day 0 is exactly the same thing. And you see that actually this motif starts to build up a few days before the event. And so we have precursor in our motif space of the cold spells. This is also true for the heat waves, but of course there will be different motifs to look at. Not that when you do the same game with some of the same game with decomposition on weather regimes, you also have, as I was saying, the information, high, lows, but it's all mixed up. And instead here you really see what you, for example, you could define some threshold in winter to decide, well, if I have the 3 motifs above this threshold, maybe there is a certain probability that we have a cold spell. So this is for extreme events. Then, of course, we can also analyze the evolution of the weights in time. So this is really to do climate change, for example, and we can see that two highs are particularly increasing, although you see there is some break here. So we cannot say that this is climate change or it's interdecadal variability, but it's a signal that we can picture with this technique. And some other motives is decreasing that actually they are more or less the complementary negative pattern. And in fact, you heard a lot also this year about the dry spell and the drought in the Mediterranean, especially in Italy right now. It doesn't rain since December, and this is expected, according to the IPCC report, to be more and more true in the future. And well, in fact, dynamically, we see that these two motives are gaining weight, and they tend to appear, let's say, more frequently than these two guys. So this will make sense from the climate change point of view, although to be sure that this is actually a real signal of climate change, we have to try it in the climate models and see, for example, if this is still all true. So you see here, I'm to the conclusions of this talk. And well, I gave you a way to go from this technique, LDA, to gridded atmospheric observables, and this we will try with Luca, who will begin its PhD thesis with Beranger and myself next October. We will try to mix variables because nothing tells us that. So when we construct the words, we can put whatever we want, okay? So the nice things here, we just test on sea level pressure. But one thing that we can do is to mix variables and have motifs that span, for example, sea level pressure, precipitation, temperature, and see really, and give us really this sort of reading of the map of the weather as a meteorologist will do it. So what is important, and I didn't say also, that if we use it in a generative way, we can also use the LDA in a generative way to construct fake fields that have the same distribution of the original one. This is also actually pretty good, and it allows to make extreme events that are realistic, so extreme cyclones and anticyclones. And it's better than what you will do trying to reconstruct your fields with EOF or POD, because they will make it they will tend to make it too smooth. So this is also telling you, and I didn't show it also, but that of course, if you use a norm L2 to evaluate your motives versus, for example, the decomposition in the EOF space, the EOF will win because it's optimized there. But if you take a metric to track the position of the minimum or the max in your field, that is what we are interested in studying extreme events, then the LDA is better. Plus having this advantage of interpretability. And then you also see, you've also seen two applications for extreme events and climate change. Now the challenge will be also to apply to convection, because in convection there is exactly this problem that if you do decomposition using EOF or Fourier, you tend to generate precipitation where it's not, and instead the convective pattern, the storms are very localized. So we don't want to generate precipitation in Lyon if it's just raining in Paris. Keep the sun here. By the way, this morning was sunny also in Paris. And that's all. I just want to finish with an advertise if I have 1 minute. We have a very nice European project, XAIDA, that is running for 4 years. In Europe with many European partners. We are organizing a summer school at ICTP in Trieste on artificial intelligence for detection and attribution of climate extremes, where you will hear about LDA and many other techniques. It will run from the 20th of June to the 7th of July. And the venue is not the Miramare Castle, but it's very close to there. There are a very nice list of speakers, but and very nice organizer. But what is really important is the food is good and the beach is not far. And no, actually, what is really important is that it's completely funded. So if you come, you have all paid. Okay, then I'm done, and this is to keep in touch, and you will have also Luca's contact if you want more answer or you want to try the code. It is a Python code on your problems. And I finish with a list of reference, and you will read our paper in where is it? It was here. You can read our paper in GRL in 2 weeks' time, because now it's in press. Thank you very much.